Hello, this is going to be a lecture on model-based system engineering using SysML, the system modeling language. And I'm going to be leveraging a lot of really good information by the author of this textbook called SysML Distilled. And also these lecture notes are based on stuff that he had provided. And so his name is Lenny Delegati. And so if you don't have this book, I'd recommend that you get it. It's worth the investment. So what it does in this textbook, it provides an overview of model-based system engineering, or MBSE. It also provides an overview of the system modeling language and provides examples of this, just suggest evidence of the return on investment that MBSE can have over traditional model-based approach, and shows further examples of MBSE tools. I'm also going to go through the SysML diagrams, and I'm going to be following the information that Visual Paradigms provides, which is the very easily available tool. There is a community edition for non-commercial use that you can try. And so first of all, we'll give an overview of MBSE and thinking of SysML in that process. And so MBSE, model-based system engineering, is a formalized application of models to support system requirements, design and analysis, verification and validation activities, beginning in the conceptual design phase and continuing through the development and later life cycle phases. And so that's something that was defined back in the system engineering vision from NCOSE. So keep that in mind. And that was done a while ago, trying to think for 2020, which is past, but still relatively speaking where we're at right now. So MBSE is not a process that does not replace existing process sets. It can be adopted by any organization to develop and maintain systems with higher quality and reduced costs while fully complying with existing process sets. And so there's three pillars of MBSE: modeling language, modeling methods, and modeling tools. And we'll start to get into that in terms of modeling languages. The object management group has adopted many modeling language specifications, i.e. grammars, that have become the de facto standards for the various engineering domains. And so there's DODAF and MODAF. Those are things that are out there. The system modeling language, SysML, and that's what I'll be talking about more than others. There's a UML model, universal modeling language. SysML is derived and extended from that. There's also MARTI, the modeling analysis of real-time embedded systems, plus the business process modeling notation. And there's many more, but those are some of the key things that to think about. For modeling methods, there are several well-defined modeling methods, and COSE has defined the object-oriented system engineering model. JPL with NASA has a state analysis. Lockheed Martin has a model-based system engineering method. IBM has several different types of systems that are out there, and as well as others. So the caveat is no out-of-the-box method will meet a project's specific needs and goals. Planning for a model-based project requires customization of a method. So there's no one-stop shopping, but it's definitely going to be helpful. Here, in terms of modeling tools, here are some examples of commercial grade modeling tools. And so these are the industrial and at times very expensive types of tools that are out there. IBM Rhapsody, Magic Draw, Atego, Artisan Studio, Altova UModel, and Spark Systems Enterprise Architect. And so each one has its pros and cons. The ones that I'm more familiar with are the Enterprise Architect and Magic. And you'll get a chance to see that through some of the material that I'll be sharing from the Delegati with the model that he created. So There are the commercial grade tools that are out there, and there's also some open source, Modelio and Papyrus. Modelio, unfortunately, has not been updated for over a year, so it is now officially stale. It no longer works on current versions of Mac OS. So it still does work on either Linux or Windows. And also Cameo System Modeler. This is the one that I actually have leveraged. Delegati created a satellite model. And so although with a reader, you can actually view it, you can't change it, but at least you can get an idea of things working in a larger context. Visual Paradigms is the one that I have been using for my non-commercial use, and at least gives you the modeling. It doesn't have the executable architecture for the community edition, but it still is quite comprehensive for SysML modeling. So the output of MBSE activities is a coherent and consistent model of the system expressed in a standard modeling language like SysML. The system model is a set of elements which represent the system's parts, actors, behaviors, elements, requirements, constraints, and test cases, and the relationship between those elements, for example, the associations, dependencies, generalizations, flows, etc. The system tool is created with a modeling tool and stored in a modeling repository, or I like to be thinking of it as a database of inputs that you have created. So a model user can navigate that model repository in the tool's model browser. So we're seeing an example here in this image. So this is a view of the top level set of packages in the system model as seen in the Rhapsody model browser. A model user can navigate the model to view a specific element, for example, a SysML block representing the core layer and the relationships that it has with other model elements. So that's can be quite useful. So there's a lot of different ways and from different points of view that you can be accessing this type of information. So in terms of the model versus the diagrams of the model, in the document-based engineering approach, designers created a set of diagrams that serve as views of the system design. These diagrams are even casually referred to as, quote, models of the system. In the model-based system engineering approach, the system model is itself an engineering artifact that has an existence independent of any diagrams that the designer may create to provide views of the model for various stakeholders. That's an important fact. The distinction leads to a fundamental precept of MBSE. A diagram of the model is never the model itself. It is merely one view of that model. So you're having a rendering of the database of information that you have that represents the system model. As an MBSE practitioner builds the system model, he or she will also create diagrams to present specific views of the model. Each diagram is created for a specific purpose to address the specific concerns of a specific set of stakeholders. Each diagram presents at best a subset of the features specified in the model. Features that are not relevant to the stated diagram purpose should be deleted. This leads to the corollary to the fundamental precept of MBSE. You cannot conclude that a feature does not exist or is absent on a diagram. It may be shown in another view of the model or in no view at all. So a quick metaphor to internalize this idea: a model is a mountain, a diagram is a picture of the mountain. So the power of a single model repository, this distinction between model and diagram is a root of the extraordinary return of investment that the model-based approach offers over the document-based approach. In a model-based approach, if a requirement changes, the designer goes to a single location, the model repository, to make the necessary changes to an element. And the modeling tool automatically updates all diagrams where the element appears. There is no opportunity for incorrect data entry. Consistency across all views is ensured, and so that's very powerful. In the document-based approach, the designer has to know a priori which diagrams are impacted by the change and where those diagrams are located. he or she then needs to open each one sequentially and then manually make the same change repeatedly in multiple locations, a process which is time consuming and error prone. So some customers, in particular government agencies, are often constrained by legislations or regulation to follow a document-based engineering approach. Documents must be formally reviewed, approved, and then they're archived. In MBSE approach, the system model serves as the primary artifact from which all other required engineering artifacts can be auto-generated via the modeling tools and its accessories. So you can auto-generate requirement specs, interface definition diagrams, system and software design specs, engineering analysis specification results, and test case specifications and as-run results, which is a very powerful thing. So for language transformation, model to source code, the ultimate capability for a model-based engineering organization to achieve is to the automated transformation of SysML or UML model into production quality source code. This capability allows a designer team to use SysML and UML as a high-level programming language while simultaneously building and evolving a system model which provides system maintainers a visualization of the system structure and behavior, allowing for faster understanding and lower maintenance costs, a mechanism for performing automated downstream impact analysis when the customer submits change requests throughout the maintenance stage of the life cycle, and automated consistent updates of all auto-generated artifacts when changes are made in the model repository. So that's a quick perspective and hopefully useful to seeing the value of what we're trying to accomplish here. Now let's talk about SysML in more detail. SysML is a graphical modeling language for system engineering domain. The key word is, quote, language. SysML has a grammar and a vocabulary just like any other natural language we speak in the world. SysML is a language, quote, spoken by system engineers to visualize, communicate, and document ideas about a system's requirement, structure, behavior, and constraints. So it is not a methodology. So in survey of model-based system engineering methodologies, we see this, it's a collection of related processes, methods, and tools. A process defines what tasks must be performed. A method used here as a synonym for procedure specifies how those tasks should be performed. With that in mind, it's useful to repeat, SysML is not a methodology. The language can be used to support many different defined methodologies. So this came about in 1997. UML was adopted by the Object Management Group in 2001, and COSI decided to adopt UML as a standard modeling language for system engineering. In 2003, the UML published UML for System Engineering, jointly drafted by the OML and COSI, detailing the requirements for a system engineering for a systems modeling language. SysML development team was formed to create the initial draft of the SysML specification. And ever since that time, there's been revisions to the SysML standard as it continues to mature. Here is a taxonomy for the diagrams. There's basically 9. And so we have the behavior diagrams, we have the requirements diagrams, and we have the structure diagrams. And actually there's another one, a parametric diagram, which either can be looked at as a subset of the internal block diagrams or really as a fourth category. For behavior, there's the activity diagrams, sequence diagrams, state machine diagrams, and use case diagrams. The requirements is one of the distinctions that make it different from UML. An incredibly important thing that you have to define what exactly you're building in a system. For structure diagrams, we have the block definition diagram. We can then be further defining those with the internal block diagrams, and then we have package diagrams, how you're doing your functional decomposition. Parametric diagram shows more details. It contains the physics, the equations for the actual how things work, to what level, using a variety of equations and stuff like that. So just another view of that. So I'll just skip over that. So we'll be talking about these different diagrams, and then towards the end, we'll get into more specifics from a vendor perspective of looking at it from visual paradigms. The requirement diagram is used to display text-based requirements, the relationship between requirements, and the relationship between requirements and other modeling elements. So we get into satisfaction, verification, and refinement of relationships that are all possible. So here are the allowable SysML elements. This is from SysML Distilled, Delegati's textbook. And so we have these 9 different types of diagrams. And here is what are the allowable elements. And so if you're in a tool, it's actually going to limit what you can actually do in each one of those types of diagrams. And so that is a helpful way to make sure that you stay true to the grammar and lexicon for each one of these. So here's a sample requirement diagram. And so you have a rec ID, you have the actual text of what that is. You can have other types of things that satisfying relationship, derived relationships, and other types of things. We're also showing packages here. And so there can be at times a little bit of a blurring the lines between some of the elements. But basically, you have a pictorial way of getting requirements and the relationships between requirements with the requirements diagram. So I will be using the SysML Distilled, which they have a model of a satellite that is available, and you can actually open it in Cameo as well as Enterprise Architect with the model from the Delegati's website. And so here is a requirements diagram for a Holloman transfer. If you're not familiar with it, this is the most efficient way to either do a orbital raising or reducing the orbit for a satellite. There's basically 2 burns, one that puts it into a highly elliptical, and then another one that makes it then stay at that new circular orbit. And so here are just the requirements that are necessary for doing that. And all of these are spelled out in that model, like I said, that you can open up in a couple enterprise tools. They have some readers. You don't have to actually buy the whole tool, but you can open up one of those viewers. So that this is just one of the things that you can have. Now for package diagram is used to display how a model is organized in the form of a package containment hierarchy. Package diagram may also show the model elements that packages contain and the dependencies between packages and their containment model elements. So here's just an illustration of what that would look like. And so here is, we can see these various elements, and then we can see that there's related sub-elements that are defined, and you can actually have packages within packages. And you can either be showing those in the picture in a SysML package diagram, or you could go down to that next level through another diagram. Going back to this satellite model that Delegati has, here is the way that he decided to do a functional containment of what's there, showing the behavior, the structure, requirements, and other things that are laid out for that model. A block definition diagram is used to display the properties and operations of blocks and the relationships between blocks. Common uses for BDDs include displaying system hierarchy trees and classification trees. So the diagram kind abbreviation for a block diagram is BDD. The model element types for the diagram frame are package, model library, view, block, and constraint block. So here is a high-level simplified BDD for the Delsat 77 that Delegati has from his website that's tied into what he has in the SysML distilled textbook. And here are yet some other examples of the types of things that you could annotate with a block definition diagram. Here are yet some other examples, and this is going back to the Dell 77 SAT. One is the structure, and we have a couple different ways of how that is represented here. So this is the satellite structures and properties, and this is the structures trying to show a hierarchical view. And yet some other examples, I'll just skip over this. But these are other types of satellite-based structures that are used and shown in SysML notation. You can also include actors in a BDD, and so here we're showing that. And so that may be something that would be useful to include for the way that you're trying to communicate and show the details of a specific design. So for a summary of SysML, this is from SysML distilled. BDD diagrams communicate structural information about a system. BDDs enable expressions of the structure type of that exists internally within a system and externally in a system environment. BDDs also express the type of services each structure provides and requires, that the type of constraints each structure must conform to, and the type of values that exist within an operational system. Generalization relationships between elements allow for defining type hierarchies and design to abstractions. This is a powerful design technique that creates extensibility in system design by decoupling the clients of services from specific implementations of a provider of those services. As the stakeholders' requirements evolve over time, one can modify existing providers or add new ones with minimal impact on the rest of the system design. For an internal block diagram, it's used to capture the internal structure of a block, specifically its part properties and references properties and the connectors between those properties. An IBD always represents the internal structure of a single block. So here is an illustration of an internal block diagram, once again for a satellite system. And so this would be for a power subsystem. And going back to the SysML, some of the things here, and this is an internal block diagram for the satellite system that Delegati has defined. And so this just shows you how that would work. Here is yet another example, a structure for a subset of blocks necessary for an IBD. So the blocks necessary for an IBD of a communication data handling subsystem are shown here. So this is one of the major subsystems that you would have in a satellite. So a parametric diagram is used to express how one or more constraints expressed as equations and inequalities are bound to the value properties of a system. Parametric diagrams support engineering analysis to include performance, reliability, availability, power, mass, and cost. Parametric diagrams can also be used to support trade studies of alternative candidate physical architectures. So here is an illustration of a parametric diagram. And so this is for a power subsystem on a satellite. And so here we're showing an equation for the fuel flow. And you have the inputs, the actual from the tank, how that would be coming in, and things that would be going out, that's based on the fuel rate that is possible with the design of the satellite the way it is laid out. For a use case diagram is used to convey the use cases that a system performs and the actors that invoke and participate in those use cases. A use case diagram is a black box view of the services that a system performs in collaboration with its others. So you're trying to to see how the system is used in different scenarios. So here's an example of a use case. And so you have the actors acting on the system. And so here you see actors operating against a hybrid SUV. So you could have a driver, a registered owner, a maintainer, and as well as others, whether it be an insurance company or the DMV. Okay, back to SysML distilled and examples with the satellite model. Here's another one that talks about the Holloman maneuver, and this is the use case scenario for how you would actually execute a Holloman maneuver with flight control, payload operations, etc. And so these are the ways of how you would be expressing that with the vantage points of looking at it from a use case. Here's just another example, and this is for another one that is contained in the Delsat 77 model, and this is actually a view that I pulled out from when I was looking at the model in Cameo Systems Builder. For an activity diagram is used to specify a behavior with a focus on the flow of control and the transformation of inputs into outputs through a controlled sequence of actions. Activity diagrams are commonly used as an analysis tool to better understand the problem space and to express the desired behavior of the system under design within that context. It is not intended to be a precise specification of behavior. So what communicates with what is a temporal flow of those things? And so here we're seeing an example if we wanted to do an acceleration, say for a car. And so you have an entry point into this and you have a final exit. And so you have the possibilities of what you're doing. So you push the accelerator, you measure the system conditions, you provide the power. All of these are happening in relationship to one another. Plus you have other types of flows. Here is a sample of the activity diagram. Once again, for the model that was part of the SysML distilled. And this is for the execution of a Holloman transfer that I referred to. And so we're seeing the activities that need to take place one at a time and in a temporal fashion. This is the same thing, but just showing in the Cameo Systems Modeler. And so that's a capture of it within the model. The other one was what was from the textbook. For a sequence diagram, this is used to specify a behavior with a focus on how the parts of a block diagram interact with one another via operational calls and asynchronous signals. Sequence diagrams are commonly used as a detailed design tool to precisely specify behavior as the input to the development stage of the life cycle. Sequence diagrams are also an excellent mechanism for specifying test cases. Here's an example of a sequence diagram. And so we talked about the activity diagrams. It just talks about the relationships of things between entities. The sequence is really trying to show that temporal relationship between things, between various elements. And I think when I spoke about the activity diagrams, this is more aligned with trying to show the temporal aspect of that. So back to the SysML distilled and the Holloman transfer. So here is a sequence diagram for that. And so the propulsion system, we have the flight computer, and then we have other types of systems, the autonomous navigation system. And so we go from one to the other as it flows through that. And so we can see different types of packages that are included here, and there's a communication flow back and forth between those various elements. For the state machine diagram, a state machine diagram is used to specify behavior with a focus on the set of states of a block and the possible transitions between those states in response to a system event. A state machine diagram, like a sequence diagram, is a precise specification of a block's behavior that can serve as an input to the development stage of the life cycle. Here is an example for a hybrid SUV. And so we basically you have to turn it on, you start, and then you have the ability to have various types of modes. Either you're in idle, you can either accelerate, you can brake, and you can go from one state to another. And when you shut down, then you go into this state of off, and if you take the key off, then you get into a state of no return, which we're illustrating with that bullseye symbol. Here's a state machine for the satellite that's in the SysML distilled model. So this is for, if we say we can be starting out with an orbital insertion, we have acquisition, slew, and then we get into this on-station modality, which it'll be spending most of its time. It may have to go into safe mode periodically. And then finally, when you get to this deorbit state, this is the point of no return where you can't be getting back into an operational state. So if your mission is over, you're trying to deorbit the satellite, that's what you would be using. So MBSE in terms is useful for an analysis and provides a good return on investment, and that has been demonstrated. So we have a case study here that I won't go over in detail. And so this was a case study from LM Astronautics. And so Lockheed Martin. And so what they used was model-based system engineering to analyze a system. And so we have the various traditional type of requirements. And so you can be thinking about that. So what are the number of requirements for 4 aeronautic programs? And so you can see for an MBSE program that the number of requirements is actually larger in that kind of thing, what they looked at. This figure compares the lines of code for these programs, and for the model-based system engineering program, it was significantly larger than these traditional programs. For a quality comparison, the SAES refers to a defect caught before release. And so what this was showing that there were less defects that needed to be addressed as a result of the model-based system engineering, which was a lot better performing than these other options. In terms of quality comparison, although the model-based system engineering produced system was significantly larger than the others, its defect density was greatly reduced. So the errors was less, the quality was greater. And so here we're seeing some examples of things working out better. What about the relative cost of these 4 programs? So the model-based system engineering was slightly larger, but we can see that the quality and other measures were greater. In terms of affordability, we can see that the affordability of the model-based system engineering program was actually performing better than all these other reference programs. Okay, that's it for covering the overview from Delegati. And so now what I'm going to do is just to give a brief capture using the material from visual paradigms, I'm sorry, to give us more information and details on these 9 diagrams. So the requirements diagrams, this is an effective identification and management of requirements can lead to project success. So the requirements diagram gives a way of pictorially showing requirements and actually showing a relationship with the requirements as well. You can actually export it into Excel if there needs to be times for that. And you also can import to a tool from Excel. And so here's just a picture of what it would look like in visual paradigms of how you would have the various types of requirements. And here they're showing the actual text, the requirement ID, and the risk. You have a title, you can have relationships and things that are derived. And so there's various ways of things that you can be captured with the requirements diagram. For the block definition diagram, this is where you can be defining hierarchy. You can define the system components, classifications, and get an idea of how they're related to one another. So here is an example for a wheel assembly. And so we have the overall wheel assembly and things that are fed into that. And so we're breaking that up into various ports and various parts. For the internal block diagram, this is where we take a deeper look into a specific part or part of the design. And so here is an example of that where we have, say, for a power subsystem. And so we have the electrical power controller, the power controller unit, and other types of elements here that there are either inputs or outputs, connectors, as we're showing here. By each one of those elements in this diagram. For parametric, this is where we show the constraint blocks and the properties in which they perform. So there's equations and physical realities that we're talking about. And so this is helpful for engineering analysis. And here is an example for a power subsystem. And so you have a flow regulation of how much pressure can actually be passed through. And so we can see that this would be the physical quantities that we're embracing with this part of the design. Activity diagram is used to specify a behavior with a focus on flow of control and the transformation of inputs to outputs. And so here is an example for a hybrid SUV, looking at the system of how you can be doing the driving. And so you turn the car on. And so we have these various types of things that we can be doing as a result of some major activities by utilizing a car. Sequence diagram, and this is used to specify behavior. Temporal behavior is a big thing. You can be talking about synchronous or asynchronous type of activities. And this can be thought as similar to what movie makers have in terms of having a storyboard. And so here is an example of the interactions, say, between a driver and a vehicle. And just a top level capture of that. There's some other information that I've talked about previously and some other lectures that give a little bit more of a back and forth communication flow between elements that can be shown in a sequence diagram. For a state machine diagram, it shows a system behavior as a sequence of states that a component or interaction experiences in response to events. And so state represents a significant condition in the life of a block. And so all of the states of a system are defined, the ways that you go from one state to another, the initial state and the final state, those are all things that can be shown. So here we're showing another example for a hybrid SUV. We have the entrance into this starting an engine and the final exit, and the key is off. And so this is a terminal state, but once we're in the operate state, we can either be in the accelerating or braking mode, and we can go between these three states in this state machine. So this is a subset of you could say this is another state machine within this higher level state machine of looking at the operate mode. The use case diagrams show the system functional requirements as transactions that are meaningful to system users. And so a stakeholder would find this quite useful to make sure that the way that they intend the system to be used, that it's captured. And so here we have, once again, for the hybrid SUV, that how the driver would be having access to doing things with the car. So either operations, so driving, or having the ability to park, and the things that you can be doing in that kind of capacity. And finally, for package diagrams, this is useful for displaying the way a model is organized in the form of a package containment. And so when you do your functional layout, that you can have things in logical groupings and even subgroupings within those groupings. And so that's something that you can have. And so here is an illustration of what that would be looking like. And so say you have an automobile model, and here are various containments of different parts of that model that we can be capturing. Okay, with that, I will conclude this lecture, and thank you very much.